Good morning, everyone. This is Joel Rooks from Siemens, and I'm joined today with Jean-Frederic Ruel and Yannick Segman. And today we're going to be presenting SimCenter and showing a PCB thermal analysis in SimCenter 3D. Next slide, please. So I'm Joel Rooks. I'm the Senior Account Manager at Siemens, and I'm responsible for our overall NASA activities, and I lead the team of account managers that work with NASA. I've been with the company for 24 years now, and I've been had the pleasure of working with NASA and JPL throughout that time. So I'm going to give you a very brief overview of SimCenter 3D and what that is. So what is SimCenter? So I think a lot of people have heard of NX. NX is a fully integrated CAD/CAM CAE system. The SimCenter product line was introduced in June of 2016, and SimCenter 3D includes all the capabilities of NX CAE along with many new capabilities. Next slide. So one of the reasons Siemens launched SimCenter is because our simulation portfolio had grown rapidly through organic growth and acquisitions. And this slide shows our CAE heritage and some of our recent key acquisitions. And one of the key aspects of the slide is that Maya has been developing state-of-the-art thermal solutions since 1983. We'll be showing you some of those solutions today. Next slide. So the three main pillars of SimCenter, and we could spend several hours talking about all those pillars, but we're going to just briefly move through this and tell you what the pillars are. So the first one is our system simulation suite of products. Then on the bottom there, we have our physical testing suite of products. And in the middle, we have the 3D simulation suite. This is where we'll be focusing today. All of these products can be managed by our Teamcenter PLM system, and they can all be optimized by our HEEDS multidisciplinary optimization software. And we'll be showing you this in another presentation this week. Next slide. So as you can see, SimCenter has a very broad suite of solvers available, including Nastran. We're going to be focusing today on the upper right corner, the PCB thermal analysis, and all of this can be accessed through one common user interface, which is the SimCenter 3D user interface. So let's show it to you. Next slide. Next slide, please. So let me turn it over to Yannick Segman, who's going to give you the introduction to NX PCB Exchange and the PCB thermal simulation software. Yannick?
Thank you, Joel. So my name is Yannick Segman. I'm product manager at Maya Heat Transfer Technologies for close to 5 years. So we've been a Siemens partners for well over 30 years. So my background is electrical engineering, and I've been in the PCB design manufacturing industry before. So I'll guide through today what is PCB Exchange, so how to import the CAD information into SimCenter 3D or NX, and how you can streamline your PCB thermal simulation from the same interface. So PCB Exchange, it's the ECAD CAD design interface within SimCenter 3D. So it helps and allows you to collaborate on PCB designs with the electrical domain throughout the design cycle of the PCB. So here we split this design cycle into 3 phases. So on the left, you have the design collaboration where you actually create and design the PCB. So the schematic is completed. You can get on the mechanical side an initial placement of the board dimension, some critical component with respect to the system, to the enclosure. And on the electronic side, you're going to do the component placement, the routing. So during this design phase with PCB Exchange, you can exchange an accurate electronic representation of the PCB back and forth, and also have a robust transmission that allows you to understand the changes back and forth. So we'll get into a bit more detail on that later in the slides. Right after the design phase, before going to manufacturing, you have the design validation aspect. So again, PCB Exchange contains many tools that allows you to compare, understand the changes from the electrical domain, and very important also, before going to manufacturing, make sure that all your domains are synchronized. So make sure that your layout on the electronic side matches perfectly what you have on the mechanical side, so that there's no mismatch between the designs. And also PCB Exchange can connect to another Siemens tool called ELMA to visualize and cross-select this information within a single interface. So that's the second phase, the design validation. And then after, you have the manufacturing aspect. So when the PCB is penalized, you can again re-import via PCB Exchange the PCB panel, and this allows you to design jigs, do the process preparation from a manufacturing point of view, prepare some drawings, and do additional processing on this penalized PCB. So now on the next slide, we're going to look at, and then the follow-up slides actually, we're going to look at the design aspect a little bit more in detail. So when it comes to PCB design collaboration, so PCB Exchange, there's actually 3 different versions depending on the ECAD tools that you have. So we have a generic one, we have one that's specific to Zuken users with a custom Zuken interface, and we obviously have for a couple of years now a specific Mentor Expedition version with our enhanced collaboration that we have with Mentor Graphics and Siemens. What I think was very important when it comes to the representation that you want to have in the mechanical side is have the information that you need at any moment. So as we saw from this slide, you have the initial layout at the top. And if you require a more simplified version of the PCB with 2.5D components, a little bit simplified for what you need to do, you can have it. But if you require on the left at the bottom a very detailed PCB representation in your CAD interface with all the details of the traces, the blind buried vias, the PCB stack, the 3D geometry of the components within the enclosure, within the system, this is all possible. So you can really go between those 2 extremes per your requirement. And also what's very important is that now we're just showing this example for rigid boards, but this is the same for flexible circuits and also rigid flex with, or even with embedded components. So we support all the leading edge PCB design technology available out there on the market. Now, when it comes to importing, if we look at the next slide, there are a lot of different formats that we support via PCB Exchange. For today's presentation, I'd like to bring your attention to a couple of things. So there's a lot of information in this slide, but when it comes to doing thermal simulation or simulation in general, the file formats that we recommend would definitely need to have all the copper and stack up information. So that would be the IDX3 in our case, the ODB++, our Zuken interface, as well as our Expedition integration. So all these 4 formats allow you to perform precise and efficient thermal analysis via PCB Exchange. What's also interesting and a bit unique there is not necessarily the capability, but also the workflow or the collaboration capability that's embedded within certain formats. So if I bring your attention to the IDX3 format or the Expedition integration, we have on the last row at the bottom an item that's called incremental changes, accept or reject. And this is extremely powerful. So we'll get into this in the next slides. This is extremely powerful when you want to understand and have an efficient collaboration between the mechanical and electrical domains. And this collaboration can also be pushed and beneficial to your thermal analysis as well. So let's get into what does that mean, the incremental changes. So the IDX or the ProStep EDMD collaboration, so this is a workflow where incremental design changes are communicated as transaction between the electrical and mechanical domain. So instead of exchanging all the time the full domain information, or sorry, the full design information, just like an ODB++, The IDX workflow and collaboration allows you to exchange a baseline, which is your initial PCB design, and then advance jointly between the teams this baseline and just communicate the changes. So you can send the changes, and each domain can actually preview the change and decide to accept or reject them, and then send a response file. So we can see this from both domains and the graphic. So this really allows to not have to run comparison report. You import the file, you can preview the changes, and it really helps you understand how the changes coming from the other domain can affect the work that you're doing. So if we look on the next couple of slides, we're going to see an example of an import. So in this case, we see a connector that has moved. So the connector blue on the left is the actual position, and the one on the right is the new position. And from the interface, you can see what the modification is. You can see comments also coming from the electrical domain. So the connector needed to be moved. And then you can also accept or reject and send additional comments. So this is really kind of a conversation, collaboration that makes the design more efficient and also allows you to minimize additional medium like emails and other means to communicate changes. All of this can be done within the IDX collaboration workflow. So if we look on the other slide, we have the same mechanism that's available on the export. So again, we can do a change. So in this case, the mechanical engineer changed the enclosure. So to fit the new enclosure, we need also to move a specific LED. So we can push this change to the electrical domain to see if they will accept the change or not. And then you can iterate until you converge to your optimal design. Now, before going on the simulation aspect, just a quick word on the integration that we have with Mentor Expedition. So additional to the workflow I just described with the incremental changes that's possible, we have a much richer data model that we have between NX and Expedition, or SimCenter 3D and Expedition now. So instead of just having collaboration, for example, on the design changes, we also have additional feature and functions when it comes to synchronization of library, being able to reuse 3D models from the ECAD domain to the mechanical domain. So on the Expedition side, there are a library of 5 million parts that exist that can be reused on the NX side and created automatically as an X part. So the synchronization doesn't just happen on the design itself, it also happens on the library. And this really gives, again, a richer data model to help you with all the different issues or challenges that you might have with leading edge PCB design. So again, PCB variants, embedded components, rigid flex. Now, on the next slide, if for those of you who are not using Mentor Graphics ECAD tools or don't have access to the IDX3 format, there's still capability, again, in PCB Exchange to preview, compare, and update specific changes. And this is extremely useful for ODB++, for example. So although the format doesn't support the incremental changes, the user still has a way to understand what changed between each design iteration, each change is coming from the electrical domain, and again, make the appropriate decisions when it comes to design constraints that exist on the mechanical side. So this is the first part that I wanted to touch base on ECAD-MCAD collaboration, and this is the first step that leads us into the simulation aspect. So just to summarize, we pretty much discussed the first bullet at the top. So doing the preliminary mechanical layout on the mechanical side, doing design changes, integration with the electrical domain, and then once you have your final updated design, since you're in the SimCenter 3D environment, this opens you to the door of simulation in general. So once you have all your details of the PCB, you can go and do your thermal analysis, structural analysis, drop test, vibration, all different simulation. And obviously in today's presentation, we'll focus more on the thermal analysis aspect. So for the second workflow on the thermal analysis, well, basically PCB Exchange can really streamline the process preparation for your thermal analysis. As I mentioned before, all the information, all the rich data model that we get from the electrical domain can be reused to streamline the process on the thermal side. So with PCB Exchange, you can automatically mesh the board, create your finite element model, create your simulation file, mesh the board, mesh the component, create the simulation objects, and all the different boundary conditions required for you to run your analysis. And as Joel mentioned before, since we're all in the same SimCenter 3D integration, we have a few interesting advantages. So the first one being the Teamcenter integration. So whether you're working in manage mode with the Teamcenter PLM system or not, all of this simulation, FEM, and your different files for thermal analysis can be saved out of the box and Teamcenter. And also this also comes with the CAD associativity. So we'll get a little bit to this later in the presentation, but if you make changes on the CAD side by moving components or actually by importing components from or moving components from the electrical domain, you can push those changes with the CAD CE associativity to your finite element model and simulation files without having to redo your simulation all the time. So let's get a little bit in more detail on how we model the PCB and how after that we model the components. So when it comes to the PCB modeling, well, as I mentioned a little bit previously, we support the copper content and stack of information from multiple file formats. So whether it's the copper distribution, the signal and dielectric thicknesses, all of this is fully supported. So what we do for the interconnections, so the vias and also the traces, is that we calculate automatically via PCB Exchange the end plane thermal conductivities and also the true plane conductivities through the layers, in this case, through a discretization algorithm. And then after this information is converted to spatially varying conductivity fields that are used in the simulation. So when it comes to the copper, we have extremely powerful tools that can be used. So we understand all the net information. So if nets need to be filtered or things like this, this is all supported. When it comes to the vias, we support also all the different technologies. So blind buried vias, micro vias. And what's very interesting is that we have an option that allows you to also specify the plating thickness. So if you have thermal vias that have thicker plating, this can be specified for specific vias based on the pad stack name. And you can also decide to fill certain vias with non-conductive material, conductive material, again, based on your requirements before the analysis. So once this preparation is done, if we go on the next slide, we're going to see that we get at the end very precise, accurate conductivity fields for each layer of the board for the traces, and also we perform automatically thermal couplings between the vias for the different vias between the different layers. So again, in this case, if the information is in the file format, all the different signal and dielectric thicknesses are accurate, just like you would see on the electrical domain. So this is for the PCB modeling. Now, if we switch to the electronic component modeling, well, again, since we have all the information coming from the electrical domain, what we do via PCB Exchange is that we create a simulation object for every component. So this allows you to specify your thermal model. So in this case, we support 3 different thermal models. So the 0 resistor, 1 resistor, and 2 resistor network, just like the JetX standard. And this also allows you to specify additional attributes and variable like the dissipation, if you want certain components to be monitored during reports, all of this can be set in that simulation object. Now, in order not to do this manually for every component, we have the concept of a component user catalog that exists in PCB Exchange and also through the SimCenter environment, SimCenter 3D environment in general. And this really allows you to specify and automate all the thermal properties that you require for your analysis in this catalog. So if you want to have a one-to-one match, for example, all the reference designators listed here for specific design, it's possible. But if you want to have a more smaller, more efficient catalog based on part numbers, different types of package, this is also possible. So the catalog can be customized. It's easy to use through different designs in your organization, and you can edit this catalog within the SimCenter 3D interface using Excel or also directly from the XML. So this, again, allows you to put the load, the maximum temperature, all the different attributes, and build your catalog, again, based on your library requirements. So if we go on the next slide, I guess this is, I believe, the last one before we go to the demonstration. But what we discussed so far is more a PCB level thermal analysis. So we've done the PCB collaboration at the board level. We generate from PCB Exchange the thermal model for your PCB as well. But most likely this PCB is used in a bigger system with multiple PCBs. And you want to be able to capture that in your simulation. And what's extremely powerful in SimCenter 3D is this concept of assembly FEM. So everything that you generate at the board level and PCB Exchange, so for example, you could do a preliminary thermal analysis when you just have the component placement of your PCB design to do some initial checks. Now, when you have the final routing of the electrical domain, you can still run another analysis with all the good information. And then after, all this information is not lost. You can map it and introduce it via the assembly FEM at the system level. So you import all the board model, the board level model that you generated, and also the loads and the boundary condition. And this is something that we will show in the demo shortly with Jean-Frédéric. So with this system level information, I think it's time to pass it to you, Jeff.
Thank you, Yannick, for this introduction. So let me present myself. My name is Jean-Frédéric Truel. I'm an application engineer at Maya HDT. I've been working there for the past 8 years, if my math is right. And I'm one of the application engineers that uses PCB Exchange and Space Systems Thermal, as well as electronic systems cooling, which are the solver environments inside of SimCenter 3D that we're going to be demonstrating today. So I'll be starting by going over the PCB level thermal analysis, and then we'll go and include this PCB level model into a full assembly for both space application as well as a Earth or manned space application with where convection is more important, obviously. So, but first, what we're going to look at is a single board analysis. We're going to be using this board that we're going to get ECAD information from our ECAD or electrical engineer friend in the ODB++ format. As Yannick mentioned, we could have used any of the other formats supported by PCB Exchange. I just happened for this demo to be using ODB++. This will give us the board geometry as well as the component simplified representations that you see on the right there, the yellow cubes. We will also get in that ODB++ file the copper and the dielectric coverage, as well as the PCB stackup. Every layer will have its own thickness. We will use this to compute the board orthotropic conductivity fields for every layer. We will also customize and use a custom component catalog that we've made for this board, where we have the component thermal information stored based on their package name and part number. We will then ask PCB Exchange to automatically mesh our geometry, as well as applying the board and component material properties and the appropriate boundary conditions, and we'll be able to solve the model that will be generated by PCB Exchange. We'll get component case and junction temperatures, as well as temperatures for every layer in the board. We then would be happy, we could do our report, but our electrical engineer colleague is still at work and he's changed our design. So he's going to send us a new design, which will compare to our current model, and we'll be able to update our simulation by using the compare and update tool inside of PCB Exchange. And this is how you would iterate on the design, going back and forth between the electrical engineer and you, the analyst. So without further ado, let's stop the PowerPoint and go over into SimCenter 3D. We're going to start off this demo here by creating an empty part file in my temp directory. Our first step, as I mentioned before, is going to be to import the ODB++ file. So I'm in PCB Exchange right now, and we're going to browse to the ODB++ that was sent to me. Go. This contains the this contains the board geometry, as well as the component geometry, as well as these component metadata. So for every component, have their reference designator, their package name, and their part number, which is going to come in handy when we use our thermal catalog to associate thermal properties to this board. But before we get to modeling the components, we're going to look at the board thermal conductivity. So I'm going to be looking at, once again, the ODB++ file. This ODB++ has all the stack-up information, as well as all the nets. So I have here in this dialog a list of all the nets on the board, which I could decide to filter some of these out if certain nets are not important for my analysis. I also have a list of all the different types of plated holes in the design based on their pad stack. So you can see in this particular board, I have 2 via types and 1 mounting hole type. The vias have different diameters, and I can choose how I want to model their plating. So, for example, I have 2 via holes. I know that my smaller via hole here, I actually want to model it as if it was completely filled with copper. Meanwhile, my other via holes, and the larger ones, and the mounting holes, I want to keep simply as plated with this plating thickness, which corresponds to 1 ounce of copper. And so that's what we're going to use. I'm going to have the software calculate the orthotropic board conductivity for each layer of the board. What the software is doing is that it's generating images for each of the layers based on the information in the ODB++. So for each layer, we're getting images like this. What we see in blue is the copper content of the board, and in red is the dielectric. What the software then does is it discretizes these images into small cubes, and each of these cubes will get their own Kx, Ky, and Kz conductivity values, which we will build XYZ varying orthotropic field from. So as you can see, for each layer in the board, each signal layer, or power or ground layer, I have the different copper contents. If I go to the bottom here, I start getting via images. So what we see here is in green is the copper and red still the dielectric. We can see that the larger via holes have a very small plating corresponding to 1 ounce of copper, and we have our smaller via holes that I specified as being completely filled in with copper. And so that's how we're going to be taking into account the board thermal conductivity. Our next step is going to be to look at our electrical components and how we're going to model those. And so we're going to use this component catalog. We have essentially different entries in this catalog based on the package name of the components in this design. The catalog contains the resistor model information, so 0, 1, or 2 resistor model, and the various resistance needed, so junction to board, case to board, and junction to board as well. We also have dissipation. This would be a nominal dissipation, but this is something that we can easily modify at the simulation level. And then all the other thermal information that you might need to modify per component. Now, we can modify these values directly in this UI, but it's often more easier to modify these values directly in Excel, and so that is also possible. For example, and so we can modify things in Excel or in the UI. So we've got our component in thermal information defined, our board thermal information defined. So we're good to get PCB Exchange to create this model. What PCB Exchange is doing is it's meshing the board as well as the component. It's applying the orthotropic fields that are defined for each of the layers to the board mesh, as well as the PCB, the stack up, so the different thicknesses. It's going to apply the component information based on the catalog. So based on the package name, the appropriate thermal properties will get applied. It's also going to apply a default convection to environment boundary condition. And this is simply to have the model solve, but we can modify that and change it with something that makes more sense for analysis. So here's the model. We have our mesh of the board and the components. Let us look at the how the board was modeled. So if I edit the mesh, I can see that the PCB is modeled with the PCB stack property. This is a special kind of mesh that essentially is what we call a multi-layer shell. So you'll probably notice that this board is simply meshed with 2D elements on the top. But internally, when the solver is going to run, each of these layers, this 10-layer board, is going to get its own copy of this mesh with its own trace coverage applied to it. So here, for each of the signal layers, we have these fields that are referenced. And I can have a look at these fields. They're right here. So for example, on layer 1, if I display this field, I'll see a similar image to what we had previously in the report. Right? And those red and blue images. So each layer is translated into a field in this board representation. Next, let's look at the components. So each component got its own simulation object named with the reference designator. And they have the resistor model as well as the dissipations that were defined in the catalog, which you also have access to here directly if you wanted to change a component to another one in the catalog. And you can obviously manually change any of these values. You could go one by one into these dialogues and update the dissipations, but you can also do so through the expression dialog, where we have all the dissipations clearly listed right here. We can edit those in Excel, but we can also edit them directly in this UI here. So for example, I can update these dissipations to be slightly higher. So that's the boards, the components, our boundary conditions. Right now, by default, we just apply, like I mentioned before, default convection to environment on the board and the components. But we don't really want that, so we're going to remove it, and we're going to replace it instead by a simple radiation to environment. For this board level analysis, this first pass at a board level analysis is probably an okay assumption. We're going to assume effective emissivity of 0.9 on the entire board and components, and we're going to radiate to a 40 C Celsius temperature. Also know that there's a card slot on the left there, so we're going to add a constraint on the edge of sink temperature at also 40 C. And now we'd be ready to solve. Let me do one quick change in the solver parameters to help this particular model along. And I'll hit solve. So this takes about a minute to go here. So we'll look at the solution together. While it's running, let me explain a little bit of what we'll see. Like I mentioned before, the board is 2D mesh in the UI there, but in the solver, we are actually getting separate meshes for every layer, and for every layer, thus we'll have temperature results. So we'll be able to probe the gradient across the board on every layer, as well as we'll get temperatures. We'll get the temperatures for the junctions and the cases of the components. I think we got a question in. Let me, while it's solving. The question is, can you model just the most significant components and then smear the rest of the heat directly on the board? And that is yes. We actually have a filter, so we can filter components based on their catalog dissipations. And so components that have a lower than, let's say, 0.5 watt dissipation, we could filter out. And then this interface here, this is the ESC SimCenter 3D electronic system tooling interface. So this is a general coupled thermal solver. So we can do pretty much any constraints or simulation objects that we want. So we could create a load, essentially, a thermal load.
Hey, Jeff.
Yep.
There was a question from Dan. Want to know if you can model the most significant components and then smear the rest of the heat directly onto the board.
Yeah, I just answered it.
Okay.
Yeah, but thanks. Yeah. Okay. So that's how you would model that. Now, while I was talking, the solution ended, so we can look at our results here. So we do get elemental results, and if we can see we have a max temp on this component here at 121 C, and if I just show the board, this is where you can see the different layers. So this was a 11-layer board, so every layer has its own temperature field. So in addition to this contour plot, we also, if I browse, we also get a report in HTML format. Here we go. With the components junction and case temperatures, and any temperatures that are above a recorded max temperature in the catalog, they are highlighted in red, so you're sure to not miss them. And these are the small components we're seeing here on the left. Now, so that's how you would do your PCB thermal analysis. All is good and well. I can start writing up my report, but my colleague, the electrical engineer, hasn't been, on vacation. He's actually been working, and he sent me a new design. So I have to, start again. But PCB Exchange has the compare and update tool that lets me compare this new design that came in to my model right now. And I can see exactly what's changed and choose to update my model or not. So if I run the comparison on the new design that was sent to me, we can see that the IC1 DigiKey component got moved. And we can preview that change. So you see that the component has moved slightly to the left there. And so we can go ahead and update our model with this change, which will move the component. And we will be able to then update our our simulation and rerun our analysis. So inside this create ESC solution, I have the update options. I can update my components or update my board, because obviously often if this component moved, my board probably updated its copper content, so we could also update the board. Right now we'll just update the component for this demo. Oh, right, I just need to tell it which files to update, because you can have multiple models for the same multiple simulations for the same part file. So I'm just pointing to the correct simulation model. And PCB Exchange is going to update my mesh and boundary conditions. And then we'd be good to go. Rerun our analysis, get new temperatures, compare the two results, and we could iterate with our colleague, the electrical engineer, and get to optimized design. Here we go. So we have the mesh updated as well as the boundary condition for the component. If we go back to PowerPoint here real quick, let's do a review of what we just saw. So we imported our board design using ODB++, or we could have used IDX or GenCAD even to get the board geometry as well as the component geometry. From this ECAD file, we got the copper content for the board as well as the dielectric content for each layer. We used that to compute conductivity values for each layer. We also used the component catalog to build up our thermal properties for the components on this board. Finally, we let the software mesh the board as well as mesh the components, applying the boundary conditions automatically, which saves us a lot of errors. If we were manually editing this, it's very prone to errors. Trust me, I've done it. And then finally, we ran the model, got temperatures. We're just about to write a report when our colleague sent us a new design. We compared it to our existing model, updated the design as well as our simulation, and we're able to rerun the analysis at that point. So that's how we would handle PCB level iterations. However, at some point, once the design is mature, and less of these iterations might happen, or even early on, we probably do need to include these PCB models into a larger assembly. And this is where our next demo is going to take us. So we're going to use the model generated by PCB Exchange and include it in our CAD level assembly of first, we're going to look at a rover. So I have a full rover, a rover CAD model for this demo that has two drives for the wheel train, the drivetrain, that uses this board as a motor control unit. So we're going to use the CAD that we generated using PCB Exchange and place it into the existing NX CAD of the rover. We're then going to use this CAD, this assembly of CAD, to create an assembly stem of the model. So we already have different element models for the board and the components. And we're going to add the PCB model that we generated, reusing the mesh, the material properties, as well as the boundary conditions. Yeah, so complete data reuse. And then we're going to apply, the only thing that's going to be left to add is going to be contacts between the board and the existing assembly. And we'll be able to run the model to get, once again, board temperatures and component temperatures, but now take into account the surroundings of the rover. And so this is the rover model we'll be using with some solar view factor results. And after that, I'll also show you an example of placing the board in Earth or terrestrial application where there's actually air. So convection is important in those cases. So we can run a couple thermal flow analyses using PCB exchange PCB models with full CFD code. So back to SimCenter. Let me. So our first step here is going to be to open our rover model. This one. This rover is a Mars rover that we already have essentially most of the model completed. It's simply missing the PCB board. In this model, we already have certain contacts created between various parts, as well as a radiation enclosure and a solar heating simulation object. So we're actually modeling the sun orbit in the Mars sky and getting the solar view factors and solar loads, as well as the atmospheric diffuse sky. Well, this is Mars, so maybe not as much, but the diffuse sky radiation as well. So, so this is the model. You'll notice that it's built using the assembly FEM structure. So each, essentially, it follows. The assembly FEM is a similar concept to the assembly part, or an assembly concept in a CAD model. Each part in the rover has its own FEM that is built up as separate components, and we're going to add the PCB model that we just generated into this assembly of models. So let us make the CAD assembly the displayed part here, and what we want to do is find where the PCB is mounted currently. So it's inside this motor assembly. So if I hide the other objects, we can see there's two of them in the model right now. And if we take a closer look, essentially, I rotate the model. There's already a board here. That's where our board wants to go. So we're simply going to go ahead and replace this default board with the PCB exchange model we created earlier. So replace component, and we'll go to the PCB model. And here we go. We have our board in the correct location with our simplified component representation. And so our next step is going to bring into, now we brought in the geometry, we're going to reuse now the simulation mesh and different boundary. So we are going to switch applications and go into our motor subassembly. So with the assembly FEM, we can do sub-assemblies. So I have this sub of the motor assembly, and essentially for each of the parts, I have separate models that are mapped to their location, and I'm simply going to go ahead and do the same thing for the PCB board. I'm going to map our PCB board model we created earlier in the first demo, and it's going to snap into the correct location based on where the CAD geometry is. So that's how we reuse the model. Since this is a subassembly that is repeated twice in the model, The PCB board is instanced twice automatically for us. We don't need to go and place each one individually. Now we can go into our simulation and import our boundary conditions for the PCB components, as well as the different boundary conditions. So we're going to point to our old model that we used before, and we're importing the simulation objects for both boards at the same time. So you can see that we have the various components for both the first board and the second board. I'm simply going to put all of these into a folder to clean up the model a little bit. Call them PCBs. So that's all the components taken care of. What's left to do is simply to connect thermally the board to the mounting in the model. And so we're going to create some thermocouplings between the top of the board, or the board, 1 and 2, and we're going to couple these to the heat sinks on top. So, so they're connected. Yeah, on these two small faces here. Oh, no, not there. Yes, these two small faces, sorry. Here we go. Here and here, and then I need to just select the other. Oh. Here we go. And this base. Then we'll do a conductance value, and voila, we have our conductance defined between the board's objects, the heatsink. We reused our mesh as well as our boundary conditions. We would then be ready to solve this model. I already, to save some time, I already ran this model, so let me open that up. And so we're going to get the board temperatures in the context of the rover, with taking into account the solar heating. So this is the model. We're looking at the solar view factors on the rover. As the Martian day goes by, we can see the shadow moving across the Martian surface here. And that's all taken, calculated by the SimCenter 3D Space Thermal solver. And with all that taken into account, we have the board temperatures both board temperatures. One is colder than the other at, this is a transient run, obviously, for the entire day. So at the end of the day, we have one board being much colder than the other. And that's being influenced, obviously, by the rover temperatures that is surrounding them here. So we can see that we have one side of the rover being much hotter than the other. And so that's the space application. We can reuse the PCB models in a full orbital heating as well as surface solar heating simulation. But we can also reuse them in a coupled thermal flow analysis. So in an analysis where if this board was, for example, used on the space station where there is an atmosphere, or on Earth, we can also reuse the PCB thermal model the same way we did it for the rover model using the assembly FEM method, but by adding air inside. So here's the same board is also a control unit for a hand drill, for example. And in this hand drill, the air is going to be, air cooling is going to be very important. So we reused the same model and took a similar approach to what we did before. And using the electronic systems cooling environment, we were able to add CFD to this as a boundary. And so what we see here in just a second is once again our board temperatures and our component temperatures, but also the air velocities and the natural convection that's going on. So we can see here that these 6 components here that were quite hot in our initial board level model, they're cooler now because they're actually coupled to this heat sink, which in air makes a lot more sense. It's a lot more efficient. And thus, we moved our hotspot to this component in this configuration. And so if I go back to PowerPoint here, just to summarize, is we reused our PCB exchange generated geometry in our assembly level model. So using our NXCAD geometry, we reused our generated mesh and boundary conditions from our PCB exchange automatically generated PCB model into our overall rover and hand drill model. We created, all we had to do was to create extra contacts between the PCB model and the surrounding enclosure. And we were able to get board and component temperatures that were taking into account the full enclosure around them, be it in space or in a conditioned environment such as the space station or on Earth. So we had a rover and a hand drill. And so that brings us to the sort of end of this presentation. I'm just going to give you a quick summary because we did go over a lot of good information today. I hope everyone learned something, and we'll go through some questions after this if you do. So you can put them in the chat and we'll get to them. So what we saw is we started with a quick intro to SimCenter 3D, how it comes from a long heritage of successful CAE solvers, and from different acquisitions over the years, and natural growth, we've have many powerful CAE solutions all in one ecosystem. And we then, from this very large view, narrowed down onto the PCB side of things inside of SimCenter 3D. And so we looked at PCB Exchange and how it supports all the major ECAD formats, and that we can transmit data files with all the different ECAD softwares out there using ODB++, for example, IDX files. We looked at the incremental workflow as well, and the power that is IDX for collaborating between the electrical and the mechanical engineers. We also looked at how it automatically generates ready-to-solve printed circuit analysis thermal models. We looked at the component libraries, the board thermal conductivity algorithm, and we saw how easy it is to reuse at the system level. I quickly talked about it during the demo, but SimCenter 3D on its own, the thermal tool itself, has some best-in-class geometry editing and associated with CAE, since it's all based off of the NXCAD software. We have advanced physics. As you saw, we can model orbital and solar heating directly in the solver with the PCB board. We have multi-physics. We can do coupled thermal flow as well as coupled thermal flow structural analyses. We take advantage of multiprocessors for view factor and for solver analyses. We saw some of the post-processing. Sorry, there's thunder outside here. There's high, advanced post-processing features. We saw some of them today. Quickly mention that this is can be all managed through TeamCenter PLM software, and we talked about the two different flavors for the solver. Essentially, the electronic systems cooling, which is aimed for more for electronics and has the CFD capabilities involved in it. And then for space applications, we have Space Systems Thermal as a solver environment. So thank you for your time today. As I mentioned, we have time for questions now. So if you want to put them in the chat, I'll try and answer them.
Thank you, JF. I thought that was a great demonstration.
Yeah, thanks, Joel.
Yeah, thank you. Appreciate you guys. I don't see any questions on the chat right now. But yeah, that was a really excellent demonstration. I appreciate it.
Oh, I do want to mention, since everyone's here, we do have another presentation tomorrow. If you're interested, we'll be looking at more in detail. So what we did with the board orthotropic properties and using fields, we can reuse some of that functionality to do a lot more in the solver, and specifically for spatially varying heat transfer coefficients or temperature fields. And so we have a whole presentation on that tomorrow morning. So if you're interested in that, feel free to join. We do have a question that just came in. how can I learn SimCenter 3D if I am new to it? Good question. So there is an extensive online help that comes with the software that has a bunch of useful information. We also have at Siemens what we call Learning Advantage, which has different classes that you can take, either on your own or with an instructor. Yeah, those are available through the Learning Advantage site on the Siemens website. As well.
And also, I'll add that if you reach out to your account manager, he can connect you up with technical resources to also help with some mentoring and learning in addition to the regular training that JF mentioned. We do not for SimCenter. We do offer student version for well, actually, let me back that up. So is our trial version for students. So if you can reach out to me, I can find out. So we can get it through our educational group. We can get you versions. We don't have a specific version of SimCenter just for students, but we can get you the regular commercial software through trials. So if you'd like to I'm going to put down in the chat, I'll put my email address if you'd like to reach out to me directly.